This video will help you to complete the lab entitled Determination of the Solubility Product Constant. As you know, the reaction you're studying is between lead and iodine ions, and we investigated different combinations of solutions of varying concentrations to examine when a precipitate would form or not form at room temperature. And then we found the saturation points, or the temperature at which the precipitate dissolved, in scenarios where a precipitate was formed. In the pre-lab questions, the first question is to determine the concentration of the lead ions in each of the solutions A through F. And as you know, the total volume of each of the test tubes, so we're looking at the concentration in the combined solution, is 20 milliliters. So we're simply looking at a dilution here. So we're going to use the dilution formula to look at the concentration. So for solution A, the initial concentration of the lead is 0.010. And you can find that in the list of materials for the lab, okay, or in the procedure, step 1. In solution A, you took 10 milliliters of that original stock solution and you diluted it when you combined it with the iodine solution to 20 milliliters. So the concentration of this solution is 0.0050 mole per liter. Now, in a scenario where you have multiple calculations of the exact same type, it is appropriate to show one sample calculation and then put the rest of the values in a table, okay, which is how it's set up in your pre-lab questions. For the iodine, okay, if we do a sample for the iodine, again, we're diluting each of these solutions to 20 milliliters. The concentration for every single test tube initially is 0.020 of the iodine. In test tube A, we took 10 milliliters and diluted it to 20 milliliters. So the concentration again for this one has been halved. If you look at the table, you can see how it changes from test tube to test tube. So in B, you took 8 milliliters of the stock. Again, you're diluting it to 20 milliliters. In C, you took 6 milliliters, D, 4, 3, and then 2. The next thing that you need to do is write the dissociation equilibrium for PBI2. And as you know from the lesson, when we're looking at solubility equilibrium, we think about the solid going into solution. So this is the equilibrium, and then we can write the Ksp expression from that. So you can manage that. Now for B, it asks us to calculate the trial ion product for each of the test tubes A through F. And as we discussed in the lesson, the trial ion product is Q. So we're looking at the relationship of the concentrations of the lead and the iodine in each of the individual test tubes, okay, as defined by the equilibrium law. But we don't have an equilibrium, so rather than calling it Ksp, we're calling it Q. So in test tube A, the example that we've been working on, we have from your pre-lab calculations, we've got the concentration of lead in that solution to be 0.005 and the concentration of the iodine to be 0.01, and we're going to square that. Okay, so what we have for this one here is a Q value of 5 times 10 to the negative 7. So for each of the test tubes, we're going to have a trial ion product. Now in the post-lab calculations, what we're doing is looking at finding K values and solubilities. So for the first one, we want to state the range at which our experimental Ksp lies. This will be at room temperature. And what you had was 6 test tubes. And for most of you, you had a precipitate here and then no precipitate here. What that means is that the saturation point for this reaction lies somewhere in this range. So you've got a Q value for E and you've got a Q value for F. Right? So you know that the Ksp actually lies somewhere within that range. So you're going to look to your chart from your pre-lab calculations and you're going to provide a range of Q values, okay, to give the Ksp for room temperature. Now in question 2, we can go a little bit further and give a little bit more information, because what you did with the solutions where there was a precipitate is you heated them up. And you heated them up to find the saturation point. So for example, with test tube A, okay, if you found, and this will vary for people, but if you found that the saturation point was 90 degrees Celsius, that Q value that you calculated in the pre-lab questions, okay, that is actually the Ksp at that particular temperature. Okay, so as you know, equilibrium constants are temperature dependent. And what you found here by finding the saturation point is you found the Ksp value, okay, for this particular reaction at 90 degrees Celsius. Now we can also go one step further and find the solubility from the Ksp, because you know that we're studying this equilibrium. Okay. We know that at equilibrium this is S and this is 2S, so we know that 4S cubed is equal to the Ksp. So you can find the molar solubility, and in this case we get 0.005 mole per liter. Okay, so for each of the test tubes where you have a saturation point, you can report a Ksp value and a solubility for that particular temperature. And if you extend this back to grade 11, this would essentially, we could use this information to derive a solubility curve. So that's essentially what a solubility curve is doing. It's monitoring the solubility changes over a temperature range. With question number 3, we want to look at how the solubility of lead iodide would be affected in a solution of 0.1 mole per liter Ki, okay, than in pure water. And for this one, you need to choose one of your scenarios. Okay, rather than testing all of them. So I'm going to test A, and in your lab, you should compare it to something different. So you can choose B, C, D, or E. Okay, so for PB 2 plus and 2I minus, okay, this is an example of the common ion effect, because rather than starting with no iodine to begin with, okay, this puts K plus and I minus in the solution, puts a concentration of I minus of 0.1. Okay, so this is going to increase by 2s, so this at equilibrium is 0.1 plus 2s, and this is s. Okay. Because our K value is so small, so we're going to use our experimental K, which is 5 times 10 to the negative 7. This is approximately equal to 0.1. Okay, so what I have here is S times 0.1 squared is equal to 5 times 10 to the negative 7. So what I find here is that the solubility is extra 0 in there. Okay, so it's 5 times 10 to the negative 5 moles per liter, which compares to our 5 times 10 to the negative 3 moles per liter, which as you can see is much smaller. So the common ion effect reduces the solubility. The last thing that you need to do is to discuss 2 what-ifs for the reaction. And make sure that you're focusing on how the error will affect the calculated solubility or the value of the Ksp that you determine either for a particular temperature or for the room temperature range.